Hey guys, welcome back to the show's version of calculus. We're doing this a bit differently. We're doing this a little bit differently since my iPad is clocked out for a little bit. So, welcome back, and today we're doing Unit 7. I have no idea what it's about, but it's a unit. Okay, so first off, we have 7.1, modeling with differential equations. Something that we have to know the difference between is direct proportionalities. We have one directly and two inversely. And directly proportional, and it's here, if A is proportional to B, then A equals K times B, and K is a constant per usual. And with inversely proportional, it's going to be if A is inversely proportional to B, then A equals K over B, or A is K times 1 over B. It is the exact same thing, where K is a constant as well. And with this entire unit, we're going to be doing everything in Leibniz notation. And Leibniz notation is basically the one where dy dx looks like this, and then you also have d2y. Ooh, that looks pretty bad. d2y dx squared and such. So yeah. Alrighty, and we're using this for this unit. This is very similar to basically setting up equations for related rates. It is honestly kind of the same things, but now we have these two little formulas to go ahead. These two formulas to go ahead and live by. So yeah, cool, great. Let's get into it with an example. Okay, so we have here the rate of change of f with respect to s is inversely proportional to x. So this one's very simple. Anytime we have rate of change, anytime we have rate of change of f or anything, that's what's going to be our df, d, and then with respect to s, anything with respect to, it's going to be s here. We're used to seeing it as dy dx, changing y in respect to x, but it's the same thing that can be used with any variable. And because it is inversely proportional, it's going to be the a equals k over b. So the constant always stays the same, and it is inversely proportional to x, so it's going to be k over x. Alrighty? And then this one over here, the rate of change of r, so rate of change of r, that's going to be dr, with respect to t, dt, is proportional to the product of s and t. Product, as we know, is multiplication. Proportional, we're multiplying them together with the constant. The proportional formula is A equals KB. So this is going to be K times S times T. So KST. Ready? And then let's go ahead and switch this up. We'll do this one down here, number 6. I'll scoot this up. We'll be doing number 6. Okay, so straighten it out a bit. The maximum safe load S for a horizontal beam of fixed width changes depending on length of the beam. S decreases with respect to L, proportional to the product of its width, the square of its height h, and inversely as its length L. This is a lot. Alright, so first things first, we know it's going to be the change of S, the horizontal beam, or the maximum safe load, and that's dependent on the length of the beam, so over dl. And it says that S decreases with respect to L, is proportional to the product of its width, W, and height. So this is actually combining both formulas, because remember A equals KB, that's algebra proportional, or directly proportional, and then A equals K over B is inversely proportional. Alright, so dl, we've got an L. So K is going to be at front here because we have proportional of the product of W, so W times H. However, at the same time, it is inversely proportional at its length of L. So, the square of its height, that's squared. Alright, and then it's going to be over L as well, since it is inversely as its length. So it's going to be over L. And that's how you do number 6, and that's kind of it for modeling with differential equations. After this, we're actually going to be solving them. So yeah, thank you.